zoiets duidelijk bij mij.
Dat klopt, dat was er wel, ja.
Ja, zo schrijven. Ja, jij moet zo schrijven.
Okay. So far, we discussed the combinatorial approach to constructing small cancellation groups. Now we will look on the geometric approach. Geometric approach is based on Van Kampen diagrams. So let me now introduce these notions.
Ja, je moet het wel goed uitzetten.
So, in general, when a group is defined by generators and relators, that means that actually it is a quotient of the free group generated by X by the normal subgroup generated by R. So one can ask the question, if we have a W in the free group that represents situation, the question is when does W belong to the normal subgroup generated by the set of relators? Actually, other both when is W is equal to 1 in the group G. So we have a vote, the question is. So the formal answer is when W is a product of conjugates of elements of R. This is a general answer. We, as I told, we can assume that R is closed under cyclic permutations and inverses in this case, so we can just write W as a word, say P1 R1 P1 minus 1 times P2 R2 P2 minus 1 Pk RK Pk minus 1 where R1 R2 Rk are all relators. So we can write, so this is exactly the answer when a group, when a word is presenting one in the group, when it is a product of conjugates of relators. Now I can present it in a graphic way. So let this be P1, R1, and cell on its boundary we have the word R1, and we return here will be P1 by P1 inverse. Then let me take the other one, P2, R2, etc. Pk, Rk, and so if we follow all these paths, so we actually read this word W. I mean starting here, going across this line, etc., etc. finally coming here. But of course, this board may be non-reduced. There could be some boards of the type x are x minus 1. So what we can do, we can perform a folding with this as a graph. Actually, we look at the vertices, and the label of each edge is a generator, and we also assume that there is an edge in the inverse direction, and its label is the inverse of this letter. Then we can perform folding of this graph. What means folding? Folding means that if we encounter two edges having a common end and the same label, then we identify them. So instead of having these two edges, we draw a new graph which will have these two edges identified. Now it actually results, and when we went this way, we have some x and x minus 1. So we have on this, when we go this way, we have x minus 1, then we have x. So it means when we make this folding, we remove from this board a pair x plus 1x, which means that we actually perform a cancelling. And so we do this consecutively until we have any possibility to make this move that is called the folding of this graph. Then actually, the final result is that we have some, in this case, two complex, because we have these edges and these two cells. Now, and then it may happen that they will be in some way connected. Maybe there are some different connected components. Whatever. Maybe here also something. So, and then when we go around, so actually the board that we read here will be just the reduced board that is coming from the original board. Because any time we have a subboard of the type x minus y, it means that we have a way to perform folding. So the graph is finite, so the process ends, and we are left with some two-dimensional complex, which we call the Van Kampen diagram. So we have constructed the Van Kampen diagram, such that on the outer perimeter of it we read the board that it is just obtained from W by cancellation. The same element in the group. Okay, when we know this will be the unit element in the group G.
So it is called Van Kampen diagram only when it's reduced, when the world is totally reduced?
When we find it, it is better to think that we perform this folding. But we do perform foldings only when it is, looking at it as embedded in the plane. So if we have, for example, possibilities to fold this and this, then we cannot do it just embedded in the plane. So we do not perform folding in these situations, only when we have these two edges are adjacent in the given embedding of the complex in the plane. And actually, we don't know. We don't know. We don't need more than this because this will be enough to have this word, a reduced word for W.
But I mean, can it happen that like you drew these two on opposite sides, but if they are in the same side, but inside one of the two cells, is it okay? It's not possible that the boundary of a two cell would have two edges with opposite labeling, right?
Consecutive, you mean?
Yeah.
No.
Because the R's are
Yes.
cyclically reduced.
Yes. Now, by the way, we might have a situation here where this is X, this is X, this is Y, and this is Y, and then we may do some surgery of it, but this doesn't concern us now. We open it and then glue it, open another way, etc. But this is just another operation which we do not need. In any case, so we have now the word presented by the outer boundary, written on the outer boundary on the two cell, and while on the boundary of each cell we have one of these relators. Let me recall that we assume that the set R is closed under cyclic words and under inverses. So it doesn't matter where we start. In any way, if we read the boundary of the inner cell, so we read just a relator from R. Okay. Now, let us consider what means the small cancellation condition. It means that a common part of two relators must be small. And if we have a measure on this relator, it should not be bigger than some epsilon. But here, the measure of all this is 1, a common part is not bigger than epsilon. It means that every inner region must have many neighbors. This is a geometric meaning of the small cancellation. That every inner region must have many neighbors. How many? This depends on what is our epsilon. If epsilon is 100, it should have 100 neighbors at least. Maybe more, but at more than if epsilon is say 1/10, that it should have 10 neighbors, etc. So then we have to look what are the properties of these diagrams when every inner region have many neighbors. Of course, it is enough for us to look on a connected component of it. So, precisely we have this. Okay. So, let us look what we have. Actually, for us it's now enough to look on the map. We even don't need the structure of the labels of it. We only look on the geometric situation that we have here. Let us do the following. For some age, for some region, let us call it, give it a number 0. Each region that have a common edge with it, let's obtain number 1. The next will be number 2. The next one will be number 3, etc. Now, we would like to ask, when we see all this, assume this was an inner region, then everything around this will have a number 1. Now, we have two possibilities. One possibility is that this number 1 just give us an annulus around this. And etc., etc. But there might be the following possibility that we have to consider. Maybe this region has not one meeting of this, but just 2 meetings, maybe more, but at least 2. This is one possibility. The other possibility is that there are 2 different regions, but they have such a way that we have this kind of features. This is also 1 and this is 1. So let me claim that these 2 situations are excluded. So, and why? So we will consider the minimal counterexample. So assume. So I mean that with maps with a smaller number of regions, we never encounter such a situation, not for one and not for any other. So I mean that we have the next one, we also do not have such a situation, etc. So this the claim is a general, we never have such, so let us consider the minimal counterexample. So let us look at the regions inside this. So they will go in these layers, and then inevitably they will have something on the top level. And every building had the highest store. Now, what happens here? We can see when it's this situation is excluded, then we have the following. 0, 1 is very simple, just here. Now, what will happen in the next level under this condition, assumption that these do not exist? Then this will be also something simple this way. Now, what could not happen that some region stands on 3 of them? Why it can't happen? Because then this region, that it is here, have 2 regions on the sides, 1 region here and 1 region here. So there's not enough regions. Even in the next level, if it would be this way, then this region have 2 regions on its neighbors, 1, maybe 2 here because the first was excluded, and 1, so this is 1, 2, 3, 4, 5, not enough. Therefore, in this kind of structure, we know that every next level stands at most on 2 of the previous level. Because if with the 3, then this should have 2 few neighbors. So let us go here. So in the upper level, we have something that it stands at most over 2. It has at most 2 neighbors and 1 above. This is 5 not enough. So this is excluded because there's a minimal counterexample, doesn't exist. The same here, the levels here, it should be a little better. We may have 2 here, 2 on the side, and 2 on the 6, still not enough. So this kind of minimal counterexample also doesn't exist. It means that so this situation, we never will encounter this situation. So we have here this kind of convexity. So we have the kind of the convex structure. What may happen? We don't know whether the next angle will be closed or not. If it is closed, very nice that we have here. Now, how much we need here? If it stands here, it needs two sides, and then one below, maybe two below. For example, if I am assuming that each one needs at least nine neighbors, what will happen? We have maybe two here, four, so it needs five above. Five above means maybe one of this kind, one of this kind, and also three here. 1, 2, 3, 4, 5, then it's maybe two below it. So this is at least here, and it's above it, we have 5 things on it. So actually it means that the number of regions will increase exponentially. What we have here, this is a discrete analog of the exponential map in the case of non-positive curvature. Okay, so when we see this, but of course it need not be full, it may be only part of it, or some parts. In each case, we give no this kind of structure. So let us look on this. We know that we have this kind of convex layer structure. Layer structure. Inevitably, there will be some highest level. So what happens here? It has at most two below him, at most two neighbors on its sides. It means that we have here the whole region minus 4 epsilon. So the length is at least 1 minus 4 epsilon. Which means that this is a kind of an algorithm relative to the measure, that every word that is equal to 1 in the group, under the assumption that we have 9 regions, I mean this epsilon less than equal than 1 ninth, then it must have somewhere in the W some part of the relation which has the measure at least 1 minus 4 epsilon. It could be pushed to 1 minus 3 epsilon if we go to the end of it, but it doesn't matter. We do not push here for best constants, just to see that in some endeavor we need the best constants that we will push for them. Here we do not push for best constants. For example, here we could take 7 and not 9, but for the convenience of argument, we will just assume 9. In any case, so we actually established that if we have a board, that never inside it in the chart we have an element that exceeds this one, so this board will be different from 1. Because if it would be equal to 1, then it would such an element of the chart with a measure 1 minus 4 epsilon, even 1 minus 3 epsilon. And we recall we have 0, 1, half lambda 0. We assume that lambda 1, that it is less than this. So we have a presentation with lambda 1, and then therefore this condition will not happen. So we knew from this argument this element is different from 1. Because element that has 1 must have a long sub-word of a relator. So actually, this makes this argument very easy. If we compare it with the combinatorial side, this is actually a much more straightforward argument. Nevertheless, we need the combinatorial argument also, and for some reasons, one of them that for the combinatorial argument we will be able to build up a ring theoretic analog, while the geometric picture so far defies any attempts to apply it to rings. Okay, in any case, so this was the construction of the small cancellation. So now, because it's so easy, let us try to do the next step. The next step should be an iterated small cancellation theory. Let us discuss first the case that we have just two groups of relators. So we consider now a group G, given by presentation, where we have R1 and R2. What we mean, R1 are short relators, and R2 are long relators. Now, what we have to impose if we wish to have an analog of the small cancellation? First of all, we will assume that this R1 satisfies the small cancellation with some epsilon. So if we have regions from R1, then their common part may not be bigger than some epsilon. Epsilon is small, for example, smaller than 1/9. Now, of course, there is some nuance that we show. When we have this, we say this condition holds unless when we take this, it also belongs to the relator. Because if such a thing, then we can, inside the Van Kampen diagram, to substitute these two regions having a common boundary with this relator, which also belongs to this set, and we just have less regions in the diagram. So we actually assuming, we may assume, not always we need it, but we may assume that if this is less than epsilon, this is one of the two. Either this is less than epsilon, less or equal to epsilon, or this is a relator. So this makes it just more covering a more general situation. Not always we need this, but it is useful to call this possibility. Okay, so first we have the small cancellation for R1. So we have the group G1, which is X over R1, and this will be a small cancellation group. Now, and then we have to impose additional relators R2, which are long relators. So, the first thing that we can do actually we can modify the set of relators R2 subject to the condition that they represent the same elements in the quotient group R1. So we need not that precise form, just we can take elements in the group that both presenting the same element in the group R1. Now, how can we use it? We can assume now that we take our relators R2 being canonical words in the small cancellation group G1. We assume we may assume that the relators from R2 are canonical words in the small cancellation group G1. But we have here to explain something. Actually, when we speak of a relator, we mean a cyclic word. So, we haven't explained what are canonical words for cyclic words. When we define canonical form, we only define the canonical words for linear words. Now, it is easy to define as well a canonical form for a cyclic word. And why? Just take a word R, take its big power. Now, let us take its canonical form. So R to the power n, and this is a canonical of R to the power n. It is not obvious in advance, it may be not true, that this word will also periodic. But let us show that if we cut a few number of periods, the rest will be periodic. I mean,
Can you say it again?
yes, I can. So we look, so now we work in the group G1, which is a small cancellation group. R belongs to R2, it's a long relator. We take an indefinitely big power of R. Doesn't matter. Very big. Maybe. So it is of course cyclically reduced. So we take. Now, we know how to define the canonical form of a word. How we've done it. It was a three-step process. We first assumed that that we take a semi-canonical form of it, just with a list of forbidden words, two long parts of the relators of R1. Then we take the certified form, and then we take the canonical form. So what was the certified? What is the certified form? It was when every of the elements of a chart had an appropriate witness for it. So, for example, if this belongs to the certified form, what does it mean? That there is a witness, that witness is this one, maybe another word, different, but presenting the same element in G1, and with certain assumptions on it. It should satisfy certain assumptions on its chart. I mean, this one, then we assume actually more than we had before. Let me recall it. We have 0, 1, lambda 0, lambda 1, lambda 2, and lambda 3, for example, half tau, etc. So we assume that this one is less or equal than lambda 3, and all the rest is some way corresponding to lambda 2 or lambda 1 accordingly to some given in advance sequence. So this was a valid witness. And then we have a one-layer map. The certified one-layer map is such that every element of the appropriate chart has a valid witness as witnessed it, certifies it. Now, I'm claiming now the following, that if we are, say, within one period from the end, and if we have a certain thing will be a certified element of the chart, then I'm claiming that if I move it by a period, which I could because it's a periodic word, then the next one, or at least a periodic one-layer map, and unless the ends. So then this one will be also certified. So if I move it by a period, or maybe it would be this way, doesn't matter, then I can have a witness for it. This is a very important argument here. It will be in more complicated situations, so let me take it the simplest one. So how I'm able to get a witness. So whatever here comes, it comes inside the one-layer map. So here we have a certain witness. I'm trying now to imitate the witness starting from this. Just, it is the same because this is by the movement by the period. But actually, because the witnesses are defined by global criterion, so maybe very distant, but what it means will be something different. So am I just mechanically moving the witness because at the end it will be different? So I'm not sure it will give me a valid witness. But in some way, it has to pass over the next instance of this word, because it's periodic. So this is less or equal than lambda 3. Now, and this witness, whatever it does, so if it comes to go through this, then I always have the safe haven, it maybe not bigger than 1/2. So let me mark the pass, because it's the safe haven, that whatever it happens is not much bigger than 1/2. So if, the point is, if I have some witness, and on some moment I'm able to switch to the safe haven, then it will be easily continued to a witness. So now, why we had this domino problem? Because it was a way that the constants in such a way that just to move to the other side, I just violated the constants. But what has here? If, let me look here, if it is on the, if it is really something like lambda 3 is much bigger than a half. So its opposite will be much less than a half. The witness may move this side or move this side. I don't know in advance. If it goes on the other side, then I can from this moment on to go to the safe haven and continue. Because this was much less than a half. Adding an epsilon just is not dangerous but the constants, and so I have this. But even if I'm going here, the lambda 3, and I have to move to the, so maybe the safe haven is the opposite side. So then, whatever the constant, I'm now switching on this point to the safe haven. Now, because what may happen is adding some epsilon to lambda 3. But the requirement of the witnesses outside this was either lambda 2 or lambda 1, which are much bigger than lambda 3. So whatever happens, when I encounter this, I'm able to switch to the safe haven and then to go until the end. And the same on the other side. Let me repeat this argument because it is a crucial argument in the whole theory. So what I'm saying, we have a word that it is periodic. We know that certain element of the map is certified. Is certified by a certain witness.
Can you just state what you're trying to prove?
What I'm trying to say that without two periods, also the certified map will be periodic. Just not looking on two outer periods, and then, of course, the canonical will periodically. Canonical is just a local competition. And if the certified map is periodic, then the canonical word will be periodic. Because when we move a period, we encounter the same competition with the same winners.
And the certified map is just the one-layer map, but where you remember only the certified.
When I know that every of the members of the chart are certified. So, well, first I have a safe haven pass, which is not much bigger than 1/2, because on all of these cells, just 1/2 is maybe plus 2 epsilon, so it is much lower than this. So there is a pass that I know that is certified. In any case,
One-layer graph, in the standard one-layer graph.
yes. So now, and actually, if I have a certain witness, no matter what, if I would be on certain place able to switch to the safe haven, so I'm just done. But what might be my problem? Because here it could be exactly the constant I need, and when I add this epsilon, so I'm above this, I cannot continue. This was my problem in general. But here what happens? Because if I'm certifying this lambda, this should be lambda 3 to be certified, which is much more strict. Now, somewhere we meet the same one. And then, if we go here, so we can switch to this. I mean, to pose this and to switch to the safe haven, because even we took here lambda 3, adding some epsilon still leaves us less than lambda 2. So I'm able to switch to the safe side without violating the constants I need that it would be a valid witness. Okay. Again, we had this valid witness here. So we try to say that if we set in some place the same member of the map.
So the first lambda 3 is the first guy in the witnessing sequence.
I know that it belongs to the certified map because it has a witness certified it. Now I'm claiming that everywhere when I encounter this multi-period, it also will belong to the certified map. Why? I'm trying to imitate the witness, just going this way, but I don't know what happens at the end. But when I meet this instance here, it just intercepts it and goes to the safe area and sends the symbols. This explains why the certified map will be periodic, maybe outside 2 periods, and then the canonical map will be periodic, maybe inside 3 periods, but n was indefinitely big. So what happens here is that except for 3 periods, this will be a periodic void. So we have actually a power of a certain void, and this power, this void will be declared the canonical void, canonical of a cyclic void. So this is a way to define the canonical void of a cyclic void.